Okay, so the reason I was asking about the number of undergrad students, I found this on Reddit, and I'm particularly interested in like if you're an undergrad and who finds this image not funny, you talk to me. Okay? So yeah, so the idea is again, I understand that this is a broad skill set, and we're here to make you succeed. So, all right. I've already talked about today's lecture plan, and I did have a stretch goal to have 5 minutes at the end, but I don't think that's happening today. So last lecture we looked at like the decoder, and the part that we haven't looked into, like how the decoder actually searches the caveats with decoding. So far we have seen that you have the logits, the decoder is outputting logits, and every time step you're picking the word that is most probable, and then you're going with that. But then that is not ideal, because in language, you can have, what we've been doing is like greedy decoding. So here you're using whatever we're outputting at each time step, and we're sort of like, feeding that back into our hidden state and then going to the next step. The problem is it doesn't have, you can back out of a bad translation. So something like, the dog jumped over the fence versus the dog jumped into the river. So let's say you want to translate like into the river, but somehow you got over, and then once you have predicted over, then you're going in that route. You're probably going to, the next probable, most probable after over will be something that can be jumped over, right? So this is a problem, and the reason, I mean, ideally, oh, this is not going to work with iPad. Okay, so ideally, what we want to have is that we want to have, in a perfect world, we would try to maximize the probability of like, E given Fs, and would take into account every output at each time step. We would be keeping track of what is the best probable path given our vocabulary. So if our vocabulary length is, let's say, 20,000 words, at every time step we're keeping, okay, so out of this V, this is the most probable, and then next step based, like, you look at that combination, and then we end up with a runtime complexity of O vocabulary to the power of T, which is not feasible. And this is the extreme case, and on the other simplistic case, we have greedy decoding, which we have been doing, and in practice, greedy decoding is like gives you decent translation. So, for example, you can argue that, yeah, but doesn't this guy, this hidden state vector, sort of capture the output word order, because we're actually feeding this here, and this is getting converted into hidden vector. So in practice, greedy decoding works somewhat good, but not great, and that's where beam search decoding comes in. So beam search decoding is the middle way ground. So instead of picking the most probable word at every time step, we keep a priority queue of our partial translations, which we call hypotheses. And then, and how many of this most probable hypothesis we keep, that is determined by what we call beam width, or the variable k. In practice, it's between 5 to 10, but for pedagogical reasons, we're gonna just use k equals to 2. And here now, you already know that what is the score of a hypothesis? The score of a hypothesis simply, it's log probability. We know this, how to do this. We just take the summation of the log probability of the output words tokens we have seen, right? So we'll take, so at every step, every decoder step T, we have a priority queue of height k, and we're keeping the top k of those hypotheses. And then we're adding one word to those partial translations from our vocabulary, and then we're calculating a new score, okay? And from that new score, we're gonna again pick the top k and move on, okay? That's sort of the repetition, like that's sort of the intuition of what's gonna happen. Now, it is not the optimal solution, but still it's more efficient and practical than doing greedy decoding. So here, I'll illustrate, the best way to explain this is using an illustrative example. So here, let's go through a beam search example. Our vocabulary is just these 3 words, H, A, and end of sequence token, okay? And our beam size is k equals to 2. And on the top right-hand side, you can see some of the notations that we will be using. And I want you this to be interactive. Please help me if I get stuck, because I don't remember what this slide very well myself. Okay, So we start off, this is our initialization, right? So here these are the two paths, 1 and 2. And in, so what is B01? What is this subscript notation? So the first subscript is our time step, okay? So here when you're initializing, it's B0, 0 signifies it's t equals to 0. And the second subscript can take possible values of 0 and 1, okay? 0 is the kth path hidden state. This is our H tilde vector, okay? And T1 is the kth path sequence. So this is the partial translation. So if I'm translating the dog jumped over the fence, so at like, let's say t equals to 2, it will be like start of sentence sequence, dog jumped, and then many, like the top k translations. Does that make sense? Like, let's go through this example first. And the last variable over here is at time t, if we extend our partial translation with a certain word v, okay? So we have dog jumped, and then over is a v, okay? So it can be over or, you know, into, whatever it is. So this is like we're extending our partial translation by one word at time step 1, okay? That makes sense? So here, at time step 0, we have three words and we have 2 paths. So always remember that in each time step we'll have kv possibilities. So if we have a number of paths, our beam size times our vocabulary size, right? So here we have kv paths. And out of this kv paths, we'll be picking, so we first calculate the probabilities and then we pick the top 2. So in this case, we're picking the top 2 probabilities, these 2 guys over here, and then we're updating our priority queue or our beam table, our top 2 possible paths, okay? Any questions? And another thing is that, you know, these probabilities, they are actually valid probabilities. So if you sum up all the probabilities, it will sum to 1. And also, we're using just probabilities and not log probabilities, which you'll be using in practice just for simplification, okay? All right. So let's move on. So now we're in time step 2. And then we already have our 2 top partial translations. Start of sequence A, then start of sequence H, and their corresponding probabilities. Okay? Stop me if you have any question at any through this, okay? And next we are extending this, our partial translation, with each of the words in our vocabulary. Again, we have then K into V possible paths. Agree? Okay. And then we calculate the new probability. So this here shows the new probability. And then again we pick the top 2. Okay? If our beam size would be 5, we would be picking 5 top probabilities from the possible probabilities. Does that make sense? Now, notice that one problem is, even though you know, this probability was really high, but it did not come into our priority queue table because there's a concentrated mass on a prefix that creates like near identical hypotheses. So because this guy over here at the beginning had a very high probability to start with, then we're seeing more of those prefixes or more of those partial translations. The others are losing out. All right. Okay, so then we repeat the process, and now we see that there is end of sequence token generated for one of the paths, and this partial path also is one of our top 2 probable paths. Okay, so when this happens, when we find the end of sequence token generated in one of our partial paths or candidates, we call it a complete hypothesis. We say that, okay, so we mark this as complete, it's done, and this is the corresponding probability for a completed hypothesis. And then we move on, and our stopping criteria, so you may ask that then when do we stop, and that's exactly where we're gonna talk about. So the stopping criteria is, it can be many different things, but usually it's, in here we're saying that we'll continue decoding until the model produces an end of sequence token for the most probable path. Okay? And otherwise, when we see a hypothesis completed, we do not change it. We just mark it as complete and we let it be, and we keep decoding until our stopping criteria is reached. Usually, there can be many heuristic measures of completion. One is, you can say that, oh, we're going to do decoding until a certain predefined time step, and then we'll stop it and see which are the most probable paths. We'll pick the top one. Or you can say that we will keep decoding until we have at least n number of complete hypotheses, and then we'll pick our top probable path. Okay? So in this case, in our example, running example, the stopping criteria is this. We stop when we have a most probable path that has the end of sequence token, meaning that in our priority queue, our top path has the end of sequence token, is a complete path. So in that case, if we find a path like that, we say that that is our translation, and we end the decoding beam search procedure there. Okay, so we move on, and then at time step t, we're again expanding with another word from our vocabulary, and we have KV paths, and from here we're going to pick the top two. Now notice that out of our in our priority table, the previous completed path is not changed; it's still there, and then we basically add this, pick one of the most probable paths, barring that completed hypothesis. Okay, so now we still have to continue because we haven't observed an end of sequence token in our most probable path. So we continue. And now, so what happened here? So what happened was that, one of our completed hypotheses is now the most probable path. So we say that this is the end of our decoding process, winner. But one problem is that, longer paths will have their probabilities decreasing. So if you go more like time steps, you're multiplying that by near probabilities, and that's going to decrease the overall probability. So it seems that if you have a shorter most probable path, it has more preference over longer paths. Now this is a problem, and you can address this problem by normalizing the hypothesis by dividing it by the length of t. But we're not going to worry about that in this running example. We're saying that our stopping criteria has been reached. We have end of sequence token in our most probable path, so we call it done. We say that we'll just return this value. This is our translation. Yes?
How can we be sure that our decoder model produces our end of sequence token?
Well, the thing is that in your training corpus, it is being trained, all the target sources have an end of sequence tokens. So, it's the question is similar to asking that, how do I know that it's going to generate a word that is I don't know, in English or something, right? So it's basically because it's trained on it, so it's trained to output. And if you think about it, if each of our training beads have an end of sequence token, and it's trained on that, then it's highly likely that it will, spit out an end of sequence token.
Would it be technically possible to generate a adversarial example where the keeps on going without generating?
Adversarial. Well, so if you can change your training data, I can think of adversarial cases where that can happen, right? But then we're in our pre-processing step, we're sort of appending and prepending, or appending with end of sequence token. So one case I can think of is that, so one case would be that if you have some kind of mode collapse, so let's say in your training data you have a certain word that is never followed by end of sequence token. So, adabra something, okay, always followed by cadabra. So then what you can try to do is that, if you somehow can have a chain adversarially that actually repeats itself, it would be some kind of, if you can mode collapse into after a certain sequence, it's always like the. In that case, I can see that happening. But then usually you'd have a stopping criteria where you said that you set a maximum value of t. So we're not going to decode after t equals to 100. So in that case, you'd have other most probable paths. And even if you do have that mode collapse, wouldn't its probability like decrease as you go through time? Because every time step, it's like something less than 1, right? Ta, 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 ta. So it's like gradually going to decrease. So it's going to fall below the top k choices. But yeah, but yeah. But does that make sense? Yeah. So this is the algorithm of the beam search, and you'll be implementing this in assignment 2. It may look a bit messy, but it's exactly what we looked at the illustrative example. Let's just block this out, go block by block, and try to understand this. Okay, so the first part is just initialization, right? So you're given a vocab V, you have a decoder. The decoder is going to take the previous hidden state and the last output word, and it's going to generate a new hidden state, right? And here we're basically, here we're just initializing the variable like b with its components. Remember, we said that we didn't see this in the example. So the zero subscript shows the kth path hidden state. So at our time step 0, which we have decoder hidden state, which is h tilde 0, okay? And the 1 subscript shows our partially translated translation. So we start off with just start of sentence sequence. Remember, in the decoder, at the first time step, the decoder doesn't know what the translated word is. We just fit it the start of sequence symbol, okay? So we're initializing it with that. And then you have the probability. So in the initial case, we just set the top, the top row of our k as probability 1, everything else as 0 or minus negative infinity. And then f is our the finished indices. Okay, so then here you're looping through, maybe I'll just add some annotations. Okay? All right, so this part, calculate hypothesis score. This is where you're updating your probability of after you have extended a word. So let's say if you're at time t, then you have extended your partial translation with a new word v, and then you're calculating the hypothesis score. So at time t, I have the dog. I'm adding jumped, and I'm calculating if my hypothesis is the dog jumped, then what did its score or probability? That's just the log probability of the 3 of the translation. Does that make sense? Okay, so we're just calculating the hypothesis score over here. And before that, here we're updating our hidden state. So we're at time t. We have, if we extend it with jumped, then the hidden state would be h tilde t plus 1. So the dog jumped. So we're just updating that variable here. And this one is our new partial hypothesis. The new partial hypothesis is the dog jumped, okay? Calculate the hypothesis, and then this is where you get, basically, remember you're getting kv possible paths. So the size of your priority queue, or your beam width, times v, all possible words in your vocabulary for each of the k paths. So in your assignment, if you're like, let's say if your k is 4 and you have your vocabulary size is 20,000, at this stage you're going to have 80,000 possible paths. Out of that 80,000 possible paths, you're going to like pick the top k probable hypothesis. And here, that's exactly what you're doing, pick k sorted. And then what you're saying is that our stopping criteria is that if the top of our priority queue table is a complete hypothesis, it's the most probable, and it has an end of sequence token, then we're done. We just return that, and we're done with the search, okay? Otherwise, we keep continuing. Okay? Any questions? Yeah.
Question about implications. So like the one
This one?
No, like the first one, like for all k,
This guy?
yeah, that one.
Yeah, so this is all our paths. Like if we have k paths, it's being 1 indexed, not 0 indexed. So we have path 1 to k. Yeah, so for all of the paths. Yeah. Yeah.
So I had a question about the complete hypothesis, which is not a dot probability. So in that case, do we take that out? Like, do we keep that the complete hypothesis and just work with the for the rest k minus 1?
That is correct.
Or do we remove that? And
No, you don't remove it. One idea is that, remember that once, because you have to convince yourself that once you have such a hypothesis, it's complete, but it's not the top. But then you're not changing that probability, let's say 0.162. But as you go more time steps, all the other paths are like decreasing because you're basically multiplying with the probability of the next word, the next word, the next word. So unless, of course, you're normalizing by like the sequence length, you don't, as the short answer is that you don't remove it. You try to fill up with the k minus 1 other possibilities until you get end of sequence token.
Okay, so at the end you'll have all the k rows.
Yeah, well, it could also happen that, let's say at time step t, you have a complete hypothesis, which is not the most probable hypothesis. You take 2 more steps. You still have, but after 2 more steps, all the other probabilities has gone down, and the one that was complete, that moves up, percolates up. And then you can end your search, and you can just return that. You can even have just 1 complete hypothesis, and that is you're done. Okay? So it depends on the stopping criteria. Or you can say that, I will keep continuing until t equals to 100, and then I'll look at which was the shortest complete hypothesis or most probable complete hypothesis, and then I'll return that. Okay? Okay, good. So this is one caveat of machine translation. So remember we talked about agglutinative languages. For example, in German, you can have prefixes and suffixes that conveys meaning or that has a lot of features packed into it, and they're usually like separated, let's say, by a dash or something. So those can be very rare. Like there could be 1 occurrence there. It could be considered as a rare word. For example, we can, in English, the closest instance would be, unfatigable, unavoidable. Like you have un and able, and you can just mix them with any verb and sort of that conveys a meaning, right? But you're probably not going to have many instances of these combinations. So this is a problem because these words can be unknown words because your model has never seen it. So usually the simplest way, intuitive way, is to break them up into subwords and basically treat them as words. It would be almost like you're treating a word like that, a phrase of words. And then you basically continuing, because the root word, like unavoidable, avoid is common. You have seen avoid, okay? Maybe you have seen on with others. So if you separate them out, then you can, it's almost like lemmatization. You have boys, you're just gonna say boy. You take the root word and then you treat everything else separately. So the most popular techniques are byte pair encoding and word pieces. If you're interested to dig deeper into it, I have the papers linked in your optional reading. If you're interested, you can read it. And also here I have some advanced neural machine translation topics for your interest. They won't be tested. The beam search, everything that we're talking about consider them as vanilla sort of pedagogical models. There's a lot of variance and quirks to each of these techniques. For example, like we looked at decoding is slow, like decoding is quadratic to the length of the sequence. So this is a problem, and there's a lot of research in this area to somehow make the translation faster. And non-autoregressive translation, or NATS, is another sort of area where they try to address that problem. And there's also a bunch of optional readings related topics. If you're interested, please help yourself. But they won't be tested. Okay, so now that we know, we have talked about every component of a neural machine translation model, we are ready to talk about evaluation. So we have our model, and how do we qualify the quality of our translations? In machine learning paradigm, you know that you always have this testing data partition which you can use for evaluation of your system, and where you have a reference translation, and you have your model's translation, and then you compared them using a metric. Now here we're asking the question, what metric to use and how to use it? Because machine translation or language translation is a little bit different from other objective evaluation like automatic speech recognition, because here the mapping is never one-to-one. So you can have perfectly fine translation, but they can be using very many different, completely different words, right? So here, as an example, we have a source Chinese sentence that has been translated into, there's a human translation, which we call the reference, and we'll be addressing the model translation as our candidate sentences. So we have two models producing two candidate translations. And if you actually read through them, then you will, as a human, you should agree that the bottom translation is superior in quality than the top candidate translation. And so then how do we objectively compare the quality of these two candidate translation? That is the question. As I talked about, that we can use some metric like word error rate. The simplest metric would be that, okay, we have the reference and we have the candidate, and we just compared their distance, edit distance, and we use that as a metric. So how many insertions, deletions, or substitutions we need to do in order to convert our translation into the ground truth reference, and that is the qualitative measure. And this works in speech translation, because if you think about speech translation, when you have an English recording and the transcription, you expect the transcription to be one-on-one mapping. You want the translation to be exactly the words it was uttered. So it's simple, right? We can do it. But in language, you cannot do that because it's never one-to-one mapping, okay? So that's a problem. One solution is, of course, to use human annotators, but that is not scalable because obvious reasons. And yeah, so here's another example where you can see that you can have multiple valid translations. So what we need is an objective measure for a subjective assessment. And this is where BLEU comes in, bilingual evaluation for machine translation. BLEU measure is very old, and there are many other metrics now used. However, it's a good measure to, for understanding the concept and the reasoning. It captures the main notions of, the quality assessment. And as I said, that you call, the translation produced by a machine as the candidate. And let's look at the different parts of BLEU now, okay? So ideally, because language can have different translations, we want to have more than one reference. So here we have 3 references, and they are conveying the same idea, but in different, with linguistic combinations and quirks. And then we have 2 candidates, possible translations. And if we, this is going to be a running example, these 2 candidate sentences. And if we actually read through them, then as a human, I should be able to convince you that candidate 1 is superior in quality. So it is a guide to action which ensures that the military always obeys the commands of the party. And the second one is, it is ensure the troops forever hearing the activity guidebook that party direct, which is nonsensical, but it has some notion of troops and what they should do. So now let's go through a BLEU calculation example and see whether this holds. The first part is calculating the Unigram precision. So we are trying to directly measure the precision of our translation to references. So we take the number of words in the candidate that has at least one occurrence in one of the references, and then divide it by the total number of words in the candidate, basic precision calculation. So for candidate 1, this is going to be 17/18, so there's 18 word tokens in the candidate, and all of them appears except for just the word obeys. So the Unigram precision is 17/18, okay? Now, what is the problem with this just using Unigram precision? There can be degenerate case. We can have a mode collapsed model that just utters the first sentence over and over and over again. So if you're just going with Unigram precision, then it becomes a problem because we can have a candidate that is just like uttering the first word, but it still has a perfect score. So in order to circumvent this problem, we cap the Unigram precision. So we say that like we'll only count a maximum number of same type words as a correct translation. So if you use a cap of 2, and then the previous translation becomes 2/7, so it drastically decreases the BLEU score or precision measure, okay? Okay, so now this idea can be generalized to as many n-grams as you want. So bigram, trigram, quadrigram, etc. So for example, if it's a bigram, then you take the number of bigrams in the candidate and you do the same thing, that how many times it appears in any of the references. And you do the same for the other candidate, and you see that it's 10/17, meaning that 10 of the bigrams in candidate 1 appears in at least once in one of these references. And here you can see that the candidate 2 is very poor. It's just the first 2 words that happens, and then none of the bigrams appears in any of the references. Okay? So now, any questions on generalization? Okay, good. So now this is not enough again. There can be degenerate case where you can have a candidate that just spits out one correct n-gram and it will have a perfect score, okay? So we need to address this issue. So in order to circumvent this, we introduce what we call a brevity penalty, that if it's too short, then we have to somehow penalize the model for a subpar quality of translation, okay? So the brevity penalty is something like this, that you take the length of the reference sentence that is closest in length to the candidate, and then the brevity term is length of the reference divided by the candidate, okay? So if the candidate is too small, then this value will be large, and then it's too brief, right? And then we apply this brevity penalty based on this equation. So this is nothing that just basically says that if it's too short, then if the candidate is longer than the reference, then don't penalize. If it's short, then the shorter it is, keep penalizing. So if you think about like in a graphical way, this simply should be, oh, this is the mark. Something like this. So yeah, so this is like the brevity value. As it keeps getting shorter, you're getting, like the penalties, you're getting multiplied by a smaller fraction, okay? So let's quickly go over, so the final score for the running example that we've been seeing. So we calculate the brevity penalty, okay? And then, so in the first case, the candidate is longer than the closest reference. So there's no penalty, it's just 1. The second candidate is actually shorter. So we calculate the brevity penalty, 0.866, 0.867, and then we multiply the geometric mean of the n-gram precisions by the brevity penalty, and we get our BLEU score. Geometric mean is like you just multiply each of the n-gram precisions and then take a square root of whatever the power is. Yeah.
How many references do we have? Almost 3?
Not always 3. In this example, there's 3. It could be 1, it could be 2. Doesn't matter. If it's 1, then you just work with 1. But ideally, we want to have more than 1 because of language differences, right? You can convey it in different ways. Okay, and this is another example of the final BLEU score on a shorter sentence. So you have 3 references, and the candidate is I Fear Dave. And you calculate the brevity score. It's shorter than the reference. And then you calculate unigram precision, the bigram precision, and then you multiply them to get the overall BLEU score. Okay, and yeah, so this is, we're not going to ask you to do this. So if you want to do a corpus level BLEU, this is already done for you in assignment, so you don't have to worry about it. So you don't take an average, you don't calculate BLEU score for each pair and then average them through the corpus. You don't do that. What you do is like you stitch them all together as source and target, and you apply the BLEU score method that we talked about. Okay? So in summary, BLEU is a geometric mean over n-gram precisions, and these precisions are capped to avoid strange degenerate cases. And it's also weighted by the conciseness of the translation. We impose a brevity penalty if it's too short. Initially, this BLEU score predicted human judgments very well, but then what happened was people started optimizing their models for maximizing this BLEU score, and as a result, correlations between BLEU score and human judgments gradually decrease. So this is a very important point as computer science students, or if, you should take note, is that whenever an evaluation metric starts to become the target of optimization, it ceases to be a good evaluation metric. Okay, so it applies to other cases in other areas of life as well. So then we have advantages of neural machine translation, which you have already, maybe you already know about this, better performance, end-to-end training, less human intervention, and so on. The disadvantages is that compared to statistical machine translation, NMT is less interpretable because of the generic nature of neural models. It's a black box you're fitting, and you don't have control over what's happening inside the black box. It's harder to debug and less fine-grained control. And if you're interested in doing neural machine translation research, there's still significant important questions in this area, like addressing the morphological differences between languages. I think most of the designs that we have today addresses the low-hanging fruit, or popular languages or similar languages like English to French, English to German, etc. But we still have to figure out lots of problems with low-resource languages like, let's say, Yupik or Cherokee, where we don't have a lot of training corpus or data set. And something that I'm very interested in using, like, grounding the meaning or grounding the translation or whatever the language task into external modalities. For example, like, instruction following by AI agents or robots, used from just non-expert language feedback, and generalization to multiple domains. So yeah, so that concludes our lecture on neural machine translation. And yeah, have a good reading week break, and I'll see you after the break.